I'd like to do two examples of infrared problems. The first one is this one, where we're given the molecular formula C5H12O, and we've got an infrared spectrum as well. So the first thing you should probably do is, since you've been given a molecular formula, is to figure out the number of double bond equivalents present. So using the method I've shown you in the units of unsaturation, what you should do is write out the molecular formula, find the effective hydrogens, and since we've just got oxygen here, oxygen won't affect the number of hydrogens, so it'll just be C5H12. Then we figure out what it would be if it was saturated, and it'd be C5. 5 times 2 plus 2 is 12, so it would be 12 here as well. So that's the saturated hydrogens. Here's the effective hydrogens here. So the number of double bond equivalents, dBe equals 12 minus 12 divided by 2 equals 0. So the compound has no rings and no double bonds in it. That's good information to know. The next thing I think is good to do is to look at the infrared spectrum and see if we can see any functional groups. And the ones I like to focus on are the OH, the CH connected to the C double bond C, the CH connected to the C single bond C, and the C double bond O. Now we know where the OH is. It's going to be a broad, strong peak in the 3500 region. We definitely have one of those. I'll put a check mark beside that. We're looking at the for CH connected to C double bond C, that would be between 3000 and 3100. I don't see anything there, and I wouldn't expect to either, since there are no double bonds in the compound. Then we better not be finding any of those. So we don't have that. CH connected to CC single bond. Yep, we've got that. That's here between 2900 and 3000. And C double bond O, that would be a strong peak in around 1750. I don't see anything there. And again, I wouldn't expect to see one since there are no double bonds in the compound, and that includes C double bond O's. So any compounds we draw, we have to draw 6 compounds. Any compounds we draw can only have satisfied this data and the data we've got here for the molecular formula. So the kind of structure I might come up with first would be something that had 5 carbons, 1, 2, 3, 4, 5, and then we could put an OH off here. And since that's all single bonded, that one looks like it's good. It's got an OH, no C double bond O, no CC double bond, so that one's okay. So we need to draw 6 of these compounds. So maybe I think about putting the OH on here, and that's okay. And then I put the OH here. But then I get kind of stuck, and I'm thinking about, well, what else can I do to form compounds if I can't use a straight chain like this? Or maybe you think of coming up with a branch chain. That's okay. Even this would be okay. 1, 2, 3, 4, 5. That would be fine too. So all of these are reasonable compounds, and we've got 6 of them. There's actually more possible. But let's look at some that would not be reasonable. Now you might say, well, what about this one? 1, 2, 3, 4. 1, 2, 3, 4. There we go. Something like that. Well, the problem with that is that there's no OH in the compound. Even though it's a legal isomer of C5H12O, it's not one that fits this data because there's no OH in the compound. So there could be no ethers present in this particular example. Alright, so that's that one out of the way. Let's take a look at another example. C6H12O, draw 4 compounds. Alright, so here's our IR, here's our molecular formula. Let's figure out the number of double bond equivalents first. C6H12O, effectively C6H12. Now we figure out what it would be if it was saturated. It'd be C6H, 6 times 2 plus 2 is 14. Alright, so that's saturated. That's what we actually have. dBE, 14 minus 12 divided by 2 equals 1 double bond equivalent. Alright, so we expect to see 1 double bond or 1 ring somewhere in this compound. Alright, so next we take a look at the infrared spectrum and we see if we have any of these groups present. These are the ones I like to look for first. So we look over here in the 3500 region for an OH. Now we do have a little bit of stuff going on here, but certainly not enough to say there's an OH in the compound. If anything, I bet that's just residual water that's in the compound. So there's definitely no OH. If we had an OH, we'd have a big broad peak in here like we had in the last example. That just isn't happening. So we don't have any OHs in the compound. Looking on this side of 3000, I don't see anything, so we need peaks between 3000 and 3100 to have this present, and we don't have any of those. That's good information because what that tells us is that if there is a double bond in the compound, it's not a CC double bond. Between 3000 and 2900 we've got something, so that would be our CHs connected to CC single bonds. And then we're looking for a peak around 1750. What do you know, we've got one. That would be our C double bond O. So there is our double bond equivalent accounted for right there as being part of a C double bond O. So we know now there's no rings in the compound because the double bond equivalent is already accounted for. Alright, so now we can come up with some structures. And we need 6 carbons, and I'll put a double bond O off here, and that will work. So that's a good possibility right there. Then I can move it along the chain a little bit. That's an example that works as well. And then you might say, well, how about we put it here? Well, if you do that, then you're going to have the same compound as we had here, so that one's not right. So the only other thing we can do now, well, you might think about putting the C double bond O on the end. Well, if we did that, what we'd have then is an aldehyde, and we'd expect to see evidence of this CH stretch connected to a C double bond O. If you look back in the notes, that's 2700 to 2900, and usually see 2 peaks in that region. So I'm looking here between 2700 and 2900. There really isn't anything going on. We're usually looking for 2 peaks that come down and look like this, and there really isn't anything there. So I'm going to say that there probably are no aldehydes present in this particular structure. Alright, let's get rid of that. Alright, now we need to come up with a couple of other examples. So it looks like we're going to have to do a little bit of branching. So that's 4, 5, and then 6. We can do that. We could vary this one a little bit. Put the double bond O off that one. That would be okay as well. So there would be our 4 compounds right there. And there might be, I think there's others possible as well, but this one might be okay. 1, 2, 3, 4, 5, and then 6. So that'd be okay too. So these are all examples that will fit the data we've been given, both in the IR and with the molecular formula.